Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight.
Throwing an interruption right at the beginning before we get into this episode. Last episode, it was all about gravitational lensing, and I had a dear friend of mine, also a geophysicist, and say that episode reminded him of the early days of Sean Carroll's Mindscape podcast. And he had one comment in the modeling part, specifically when talking about in geophysics we do two inversions, one with and one without prior geological evidence. And he made the point that it really should be constrained and unconstrained instead, because we are putting in some prior information by the way we construct how we solve the problem and how we regularize to create models that solve the physics in 3 dimensions, but do so in a smooth manner. We're making assumptions, so we're adding prior information before we've even started. And that was absolutely true, and I thought at the time it would be too technical and would get off track, and I had already had the wonderful Dr. Yorgos Vernaudos for almost 2 hours total between the 2 parts. So I kind of let that one lie, and I wasn't sure that anybody would catch me up on it, but it does. So there you go. I do listen, and I do take back that constructive feedback, and hopefully that helps clear up anyone who noticed that was missing in that last episode. Okay, back to regular scheduled programming. Here on Whimsical Wavelengths, time is geologic. The Earth is dynamic, all of it. Plate tectonics, weather, ocean currents, biosphere, cryosphere, extraterrestrial, like solar events, meteorites, nearby supernovae, and on and on and on. But the seas, they're constant, right? I mean, they exist. They've almost always existed. No, I'm not going all the way back to the proto-oceans billions of years ago. I'm referring to the Mediterranean Sea. And I hope you're up for a salty tale of a disappearing sea. This episode is all me. Why? Because I like this topic. And I think I have enough background to tell the story after digging through the literature. And I wanted to spin this in a whimsical yarn. In other words, a different way than just my average interview. But first, why is the Mediterranean Sea so confident? Because it's always making waves. But there was a time where the whole Mediterranean basin just dried up. See, it really shouldn't be so confident. And that event is called the Messinian salinity crisis. Okay, first off, historical deviation. Pliny the Elder, a Roman author, naturalist, natural philosopher, and naval and army commander to the early Roman Empire and friend of the Emperor Vespasian. He wrote Historia Naturalis in approximately 77 AD. He's a famous guy from Roman times. He describes a legend popular among the inhabitants of southern Iberia, which is modern-day Portugal and Spain, telling how the Mediterranean Sea was born. The myth, the Mediterranean Sea was deserted and cut off from the ocean, and it was Hercules who dug an inlet with his sword between Africa and Europe, right through the Rock of Gibraltar. This allowed the ocean to flow into the Mediterranean basin, where it was once excluded, thus changing the face of nature. Other writers of Western culture, like Galileo, were inspired by Pliny's account, elaborating on the scenario of a desiccated Mediterranean Sea flooded by Atlantic waters. None of these accounts were linked explicitly to the field evidence. One more thing, history-related. Geology started with uniformitarianism, or by a different name, gradualism, meaning geology happens slowly and constantly, layers upon layers over the eons. The birth of geology was under this principle. Generally, it is true. But there are large events like meteorites, glacier outburst floods, or in this instance, the Messinian salinity crisis that break the mold of gradualism or uniformitarianism as catastrophes can have a very, very large effect on the geology. Okay, now on with the show. Anyone familiar with plate tectonics will point to cycles of opening and closing of ocean basins. The formation of Pangaea, for instance, around 300 million years ago, where continental land masses came together through the closing of ocean basins, a process that took place over millions of years. And yes, that process is involved here, but it's more complicated. Or at least we can look at it in a more complicated way because we have a lot more data. The question is exactly where to start. And I guess I'm going to start with the rocks. Like everything, there is some thought that goes into where to start a story. The initial geological sleuthing work was done in the 1950s through to the 1970s. And that's when the pieces of the puzzle, by mapping evaporite deposits around the Mediterranean Sea, came into focus. But I'm going to put a pin in 1970. Why? Well, because in 1970, an ocean floor drilling program was taking samples of the Mediterranean seafloor and found salt. When put together with the other data, it was suggesting to be up to 3 kilometers thick, starting at about 200 meters below the ocean floor. So there was a problem. Where did this salt come from? And why was it there? This was the first real hard data point that something needed to change. Needless to say, in 1970, this threw a section of the scientific community into choppy waters. There was a discussion and different hypotheses were suggested and debated. In 1975, another deep sea floor drilling project put the bigger parts of this debate to bed. It was, as you say, sedimentary, dear Watson. Evidence for the Messinian salinity crisis was found in a number of different locations across different basins within the current Mediterranean Sea. It was clear that the Mediterranean Sea at some point was separated from the Atlantic Ocean almost 6 million years ago and began to dry up. Its transformation into a giant salt desert more than a kilometer below global sea level is the only model to provide a possible explanation for all of the available data. Welcome to the Messinian salinity crisis. How? Why? I mean, what happened? How did this huge basin, which stands at 3.75 million cubic kilometers of water, how did it go away? And that's an astronomical amount of water. Now, it's always tough when talking about large numbers to put them into perspective. I mean, we can look at an Olympic-sized swimming pool, which is 10 to the minus, 6 cubic kilometers, 2.5 times 10 to the minus 6. Or we could look at Death Valley. The whole valley that sits below sea level is somewhere around 670 cubic kilometers of volume. Still nowhere near how big the Mediterranean basin is. Even if we look at the Great Lakes here in my country, Canada, as well as the US, they stand at a whopping 22 and a half, a bit more, 1,000 cubic kilometers altogether. Still not even close. We can look at the Red Sea at 233,000 cubic kilometers. We're still off by a bit more than an order of magnitude. The Black Sea is a little over 500,000 cubic kilometers. See, there's just really nothing we can really look at as like an enclosed area right now on the Earth to compare just how much water dried up during the salinity crisis. The numbers are staggering. The fundamental process is that there was less water going in to the sea than evaporation. The water would have become saltier and saltier until it began to deposit it. In other words, you reached the saturation limit of the water and it began to deposit minerals onto the sea floor. This changed the environment drastically. This increase in salinity, the increase in salt. Very quickly, geologically, the changes would have been seen in a human lifetime. But the whole crisis took place over 600,000 years, give or take, where water evaporated, depositing gypsum and salt. So let's set up how all this happened before coming back to the environment and the ecology. So lots of work has been done since 1970, and it's important to note that plate reconstructions, plate tectonics, and modern science of geology is also fairly new. First published ideas that the surface of the Earth were moving around was in 1912 by Alfred Wegener, but the mechanism of how the Earth's continents moved could not be pinpointed. It also wasn't a time where we could measure them. Today we have GPS, so we can actually measure how continents move. The evidence at that time was via geography, where mountain ranges existed on different continents were lined up, geological events and layers recorded on different continents, and biologies that were similar on very different areas that are no longer connected. They were all adding up, but the mechanism was elusive. What was needed was the invention of a magnetometer that could be towed by a boat. That, eventually, when it was there after World War II, showed magnetic striping across rifts where plates pull apart. But like I said, it happened after World War II. It wasn't until the late 1950s and early 60s that plate tectonics started to be part of the bedrock of geology, and the modern discipline was born. So in many, many ways, the discovery in 1970 was early in our quickly changing understanding of the Earth and its dynamic processes. The Mediterranean basin begins with the breakup of the supercontinent Pangaea in the Mesozoic, or if you want to call it, the age of reptiles, i.e. the dinosaurs. It seems that geological time frame is coming up yet again. Check out episode 7 for a discussion about how dinosaurs maybe partially are responsible for the lifespan of us mammals, as well as episodes 9 and 10, which are all about dinosaurs specifically, the evolutionary cousins of the famous T-Rex. Okay, well, the breakup of Pangaea caused seafloor spreading and triggered the development of the Atlantic Ocean in the Jurassic period, which separated Africa and the Eurasian plates from the North American plate. Seafloor spreading started to separate the African and Eurasian plates into the Tethys Ocean in the late Cretaceous period. These African and Eurasian plates began to converge some point after that and started to close the Tethys Ocean. And the remains of that ocean basin, that ancient ocean basin, is now called the Mediterranean Sea. Today, the Strait at Gibraltar, the area where the Mediterranean meets the Atlantic, is 284 meters deep at its shallowest point, 14.3 kilometers wide. At the Tarifa Narrows, I'm sure I'm pronouncing that wrong, I'm terribly sorry, the paleogeographic reconstructions of the Gibraltar region suggest that the early Messinian Atlantic-Mediterranean connection was actually not as we see it today, but was a four-land basin system with multiple connections in and out. Four-land basin is a low spot next to mountain ranges. The idea is that the weight of the mountain range pushes down on the crust, causing flexure. This is isostasy and lithospheric flexure at work. It was only a couple of episodes ago where isostasy was explained too, although in the context of plate tectonics and Mauna Loa volcano. The back library to Whimsical Wavelengths is growing with tons of information. So these mountains create a basin or a low point parallel to it as it presses down on the crust. It seems over time these multiple gateways became just one due to some really complicated plate tectonics. Okay, so perhaps a 1/3 point summary of the episode is in order of this whimsical tale. The Mediterranean Sea is what is left over from an ocean basin that formed as Pangaea broke apart and the continents of Africa and Eurasia split apart. After that ocean had opened, it began to close, bringing Eurasia and African plates back towards each other. At approximately 6 million years ago, or 5.96 million to be more exact and precise, the sea was cut off from the Atlantic Ocean, causing much of the 3.75 million cubic kilometers of the Mediterranean basin to evaporate. The rest of this episode will be split into, roughly speaking, 3 parts, and not all of them will be of equal size. What caused it to close and what happened to the basin being completely isolated, how and why did it get connected again, and a little bit of the after effects. So what caused the closure of that connection to the Atlantic Ocean? There were at least 2 different ways in and out of the Proto-Mediterranean basin, as I already described, that closed progressively before the salinity crisis due to plate tectonics. Depending on the time we are starting from, the northern route was closing due to uplifting, or isostasy, and losing a subducting slab. Subduction is where oceanic crust from one plate is slipping beneath another plate. When that oceanic plate runs out, the continental plate is too light or isn't dense enough to subduct, and you can just leave that oceanic plate dangling down below. So what's being discussed or suggested in this instance is that oceanic plate beneath modern-day Spain detached. So it fell off its continental counterpart. No longer was this dense oceanic bit of plate weighing down, pulling down on that continental crust. So it started to uplift and rebound due to crust rebounding. South, in what would be present-day northern Morocco, the crust was being compressed, causing uplift, building the Atlas Mountains. It is clear that this uplift is caused by the African and Eurasian plate coming together, but sounds like there's some details that are a bit murky, and I don't want to go too far of a deviation to try to figure that out at this time. But what is clear is that the Atlas Mountains are starting to be pushed up in this process, and you're getting some uplift, which is eventually going to cause closure. One of these two closed, causing there just to be a single way in and out, the Proto-Gibraltar Strait. A lot of this can be traced through marine connectivity, through fossils and dating of sediments and geochemistry of those sediments. There are, of course, other effects that are complicating this picture. Starting from 1970, science has proposed competing ideas to explain how all of this happened. Our understanding has got us to the point of the story where we can say pretty definitively that tectonics was the primary driver. But one of the first ideas was sea level change. We know it can rise in a warming climate as glaciers and ice sheets on land melt. We're seeing that today. It can also rise due to tectonics. For instance, during the breakup of Pangaea, there was a lot of rifting and pulling apart, creating new, young oceanic crust. New crust is hot and less dense, so it sits higher, displacing more water, and therefore causing sea levels to rise during that time in the ancient geologic past, as much as 170 meters higher than they are today. If we get to the point that all ice melts in the glaciers and the ice sheets, we would see a total rise of about 70 meters. So we know how much sea level could have risen, roughly speaking, in these instances associated with the Messinian salinity crisis. And we can look at the climate of the time and when those sea levels should have been fluctuating. The data shows that sea level changes are not the driving force here, because it just doesn't line up with the climatology data and when there was glaciers and how we expect that sea level rise to be changing during this time. There are also feedback systems we should talk about. I mean, once we start having the basin isolated, it begins to evaporate. Isostasy will strike again, as all that mass that was there once, i.e. the water, now is not. So now you're having crustal rebound. You're having isostasy happen, so the uplift occurs, further isolating the basin. So we've got a couple of things going on here. We've got uplift to the north, we have uplift to the south, and eventually it coalesces as one in and out of the Mediterranean basin, but the uplift hasn't stopped. It continues to uplift and it's isolated. Okay, so what happens now? Well, it's clear, like today, there was less water entering the Mediterranean basin from the mountains and streams and the land around it than there is evaporation. That's true today. Meaning if isolated today, the same thing would happen. Estimates of how much water drew down during the crisis vary from 600 meters to 2,000 meters. It seems there's a local component to how much the water dropped, and the large number range is also indicative of disagreement between some data sources. Regardless, it would have changed from an interconnected sea to the Atlantic Ocean to isolated pockets of supersaline water, like the Dead Sea today. Now let's just talk about some of those numbers, like 2,000 meters below sea level. For a basin, that's just crazy. 2 kilometers below sea level. Down that far, it would be significantly hotter and more atmosphere. Way more atmosphere. i.e., you would have more atmospheric pressure on you if you were at 2,000 meters below sea level at a sea. We have a standard average measurement for our atmosphere. We can call it 1. We call it 1 atmosphere at sea level, like Celsius, which is based on the boiling point and freezing point of water at sea level. So keeping that into account, at 2 kilometers below sea level means an atmospheric pressure of 1.26 atmospheres and a boiling point of around 106.6 degrees Celsius. That's a lot of extra atmosphere. It's also like being 2.5 meters underwater, or like 7 or 8 feet underwater. It's something you can feel. It will feel oppressive. Just to keep in mind, the current record on Earth's surface is around 1.07 atmospheres. So this would have been truly a special place. But we've only really talked about the increasing of the pressure, because it will also increase the temperature. Increasing atmospheric pressure also increases temperature. And in this case, by about 20 degrees Celsius, more than at today's sea level. So let's pick a spot somewhere in the Mediterranean. No, I'm not doing this as a rigorous way. It's really back of the envelope calculations. But for this argument, I'm choosing islands just off the coast of Spain. Palma. It's an island in the Mediterranean. It's summer. Its average daytime highs in summer is 30 degrees Celsius, or 86 degrees Fahrenheit. So 2,000 meters lower in elevation rises the temperature to about 50 degrees Celsius, or 122 degrees Fahrenheit for the average daytime high in summer. In fact, it would be easily the hottest average place on the planet. It's just crazy to think that you would be at 50 degrees Celsius, have an atmosphere feeling like air 2.5 meters underwater, or approximately 8 feet. Wow. It would feel like hell on earth. Imagine all of that heat and pressure allowing for more humidity too. Near the shore of this much reduced sea would definitely feel like hell on earth. Basically anything living down there would have to be extremophiles, or if you would like a definition, creatures that live in truly extreme conditions. The salt deposition for things like table salt or halite and gypsum during this time represented maybe up to a little over 5% of the total ocean dissolved salt content. This definitely modifies global ocean chemistry, and all this salt is deposited while the water cycle continues. Much of the water evaporated in the Mediterranean would end up back in the oceans, but without all that extra salt. This in turn affects all the ocean chemistry and effectively allows it to freeze at higher temperatures because it has less salt. The effects are long-reaching, and in some cases, we likely don't even know how far-reaching it would have been. I haven't even yet got into what happened to all the life that was teeming in these waters before the salinity crisis started. As the flow between the Atlantic and the Mediterranean became restricted, there was a change in the salinity. Even today, the Mediterranean Sea is saltier than the ocean, the Atlantic Ocean. The Mediterranean Sea has about 37 grams of dissolved salt versus 35 for the Atlantic Ocean. If you swim in both back to back somehow, if you could, teleport distances or something, you'd be able to notice the difference in buoyancy. Some papers make the argument we should push back the start of the Salinian crisis to where there's a marked change in the salinity, which is manifested also in the biology of the basin and the chemistry of the water. As it became more and more restricted, the water, like I've said, would become saltier, would lower the pH and have less oxygen. So the short answer is the sea that was once full of species became pretty close to barren. Poof! The sea would have gotten hotter and saltier in a speed that there is just no way full ecosystems could have evolved or adapted to. It represented a significant regional mass extinction. Another tidbit to think about here is that the Proto-Nile River would have had to cut down 2 kilometers to reach the Mediterranean basin. The erosional processes from water draining to the basin is definitely something to think about. And yes, there's some evidence for it if you look at these incisions and stuff that have come from these rivers. So the end of the Messinian salinity crisis happened quickly, or at least we think it happened quickly, 600,000 years after it had started, or 5.33 million years ago. The waters of the Atlantic Ocean found a way through the present-day area of the Gibraltar Strait in an event that became known as the Zanclean Flood. There is agreement that this was triggered primarily by tectonic subsidence. When going through the material, I was greeted with one word all the time: sill. Specifically, Camarnal sill. Again, I might be pronouncing that wrong. If you're not a geographer or work in the marine realm of geology, I was really confused by this term. I was like, what is it? What is a sill doing? Why are they talking about a sill? Because a sill, in a geological sense, is a intrusion of magma into layers of rock. It pushes in and conforms to the same fabric of the rock, like between sedimentary layers, and then cools. That is not what they're talking about here. This is an instance where context is everything. In this case, it's probably more correct to say an aquatic sill or an oceanic sill is an area of relatively shallow depth that restricts water movement between bodies of water. In this case, the Atlantic and the Mediterranean Sea, and that feature is called Camarnal sill. Okay, before going back to the flood, why could it happen in the first place? Perhaps let's revisit the closure. Plate tectonics caused uplift in that particular instance through two general mechanisms. The mechanism I want to revisit is the isostatic rebound or crustal flexure from an oceanic slab detaching. That weight dragging down the plate was lost, and the crust began to uplift. That uplift helped isolate the Mediterranean Sea. The area of Gibraltar and the whole Mediterranean basin is a complex mash of tectonics, of different plates, microplates, of everything moving and coming together, as this ocean basin that was once the Tethys Ocean continues to close. Another ocean plate left over from the closing of this ocean is still beneath the area of Gibraltar. From about 8 million years ago to 5.3 million years, it likely became much more vertical. And during that time, it also rotated to exist beneath the area of the present-day Strait of Gibraltar. And all of this weight from this relic plate is pulling downwards, which is creating or created subsidence. Eventually, that subsidence allowed for some of the water from the Atlantic to flow into the desiccated Mediterranean basin. Well, that's what likely started out. Anyway, it started out probably like a little trickle, and then became a torrent. Perhaps it's important to think of this as a thought of experiment a little bit, using the time you spent at the beach or mucking about in a creek, building makeshift dams as children. A childhood pastime. Well, perhaps cast your mind back to that, using sand. You have flowing water. You make this sand dam as quickly as you possibly can. The water backs up and eventually overcomes the makeshift walls. And if you're not quick enough with more sand, it starts as a small water stream. But it begins to erode the sand dam, creating bigger channel. And quickly, the whole dam is pretty much gone, or at the very least, there's a big giant hole in the wall. And all that water came gushing out of it pretty quickly. It's a bit more complicated here, and the scale is flippin' enormous, but at its heart, it's the same process. The connection is made through subsidence, and to begin with, the flow is small, but it is eroding downwards and the sides, creating a deeper and wider channel, allowing more and more and more water to flow. Modeling suggests the flow rate was 10 to the 8 cubic meters per second. Yeah, I know. Numbers. Just numbers without context. It's hard to wrap your head around it. Let's give it an example. Going back to the Olympic swimming pool, which was 2,500 cubic meters in volume. So that means 40,000 Olympic swimming pools of water passing through the area of Gibraltar a second. If we just, decided to be even just as silly and look at the Nile River, at maximum discharge, that's around 7 14,000 cubic meters per second. So you would need over 14,000 Nile rivers at their maximum discharge to equal the flow into the Mediterranean basin to meet the same flow rate modeled for the end of the salinity crisis. The Zanclin flood, the mega flood. 14,000 Nile rivers. That's just crazy, just to equal the flow. It was so fast that at peak rates, the basin sea level could have risen by as much as 10 meters a day. Absolutely staggering. And the modeling suggests that the bulk of the refilling would have happened over a few months to a couple of years. There is some serious scars of erosion and of this flood that are visible. However, they are underwater. The dimensions of the inferred megaflood make it the largest known flooding event on Earth. 1 to 2 orders of magnitude larger than the well-documented events induced by the Northern Hemisphere ice sheets, disintegrating and creating the Missoula floods. And yeah, that's a story for another time. Definitely would want to get an expert in to do that. I should also pause and say there are other ideas on the speed of the return of open marine conditions. There is some nuance in the data, and some, to this day, even in 2025, argue for a more gradual return to marine conditions. And to be fair, a more gradual return fits some of the data. However, it's my personal opinion that the physical evidence supports something fairly fast happening. 10 meters a day rise in sea levels fast? Well, I don't know, but fast all the same, especially when we're starting to look at geology-wise. It would have been drastic. So the sea ecology was all wiped out in this crisis. Completely gone 600,000 years ago, and poof. And now the water is back, boom, and it can be colonized again. Work on the fossil record suggests that species diversity was decreasing before the salinity crisis happened by the actual isolation, dropping by somewhere around 14%. Also, looking at the fossil record, again, with the caveat that the fossil record is always going to be incomplete, but of the 2006 distinct marine species recorded in the pre-Messinian salinity crisis basin via fossils, it seems only about 86 were able to survive till the end of the crisis. That is amazing. That's so much. All those species just gone. In terms of size or the amount of salt deposited during the Messinian salinity crisis, it's small in comparison to past events, where ocean basins were closed, causing seas to dry up. Some great examples of these giant salt events are from the early Cretaceous and the middle late Jurassic. However, when we start looking at these older events, we can use this one, the one from the Mediterranean basin, and how it reshaped the Mediterranean ecosystems as models to understand these much larger events and their associated extinctions at those times. We can use this event because we know it's so much better. It's so much newer. We have all of that information at the Earth's surface still. We still have access to it. The further we go back, the more it's eroded, the more it's faulted, the more it's mashed up through plate tectonics and altered. But we can use this event to start looking at those much bigger events of the past and how they would have reshaped things like climate and the biosphere. Well, I'm going to call it quits there on this story. Write to me. Write the show. The email's in the show notes. Maybe you want part 2 to this, another way of looking at it. Maybe you want to bring a guest on to tear all of this apart. I don't know. Maybe you have an idea for another show topic. Write to me. If you haven't already done so, subscribe. If you've gotten this far and listened to the whole thing, then obviously this is up your alley and you need to subscribe. And yeah, I think we're going to come right back with some more looks at the cosmos in the times ahead. I'm constantly working at new guests. If you happen to be a researcher with peer-reviewed research and you want to share it here on Whimsical Wavelengths, or you know someone who's recently published, or maybe they want to talk about their thesis, get in touch with me. I'm always looking for new ideas for shows. All right. See you in 2 weeks.
Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight. In a world so chaotic that misbehaves, melodies that echo show us sex always. Colors intertwine, painting the sky. We're lost in the rhythm as the universe flies by. Oh, we're tuned in, feeling the beat of the unknown. Can you hear it? It's echoing through your bones. In this melodic maze we